So when I was asked a month or so ago by the organizers to give the closing remarks, my first reaction was to decline because there's so many other people with closer and more personal associations with Stephen than I have. But before I could come up with the right words to politely decline without seeming rude or inconsiderate or whatever, I was thinking, well, I've really spent an extremely high fraction of my scientific career working on ramifications of Stephen's ideas. And I really would like to say a few things about his work. So here I am. Now, the charge in the original, it wasn't really a charge, it was a suggestion in the original email from Harvey in terms of what they were looking for. I've written it down here to quote exactly, is that this could perhaps be a broad summary of what was discussed at the conference, the importance of Stephen's work, and some discussion of future prospects. Okay, so I'm going to skip the future prospects. Yogi Berra has already pointed out that predictions are difficult, especially when they're about the future. And I've noticed that my predictions are not better than average, so I'll spare you that. And let me move on now to a broad summary of the conference. I think this has been a spectacularly great conference with a lot of really interesting, great talks on very interesting topics. And indeed, I think we should give Harvey and the rest of the organizing committee another round of applause for such a Okay, that completes my conference summary. And now I'd like to move on to saying a few, well, relatively brief things, not as brief as those, about Stephen's work. Well, I mean, Stephen would be rightly incredibly famous if he had never worked on particle creation on black holes, just from his other major contributions to general relativity, and, well, quantum gravity, other ideas. But the paper he wrote on particle creation by black holes, which is what I want to talk about, is, I mean, without question, the most amazing paper I've ever read. Mihalis was plugging Hawking's books, so I'm going to plug the paper here. It's a 20-page paper in Communications in Mathematical Physics. Well, everybody in this room knows that it's a great paper, an amazing paper, but I don't know that everybody knows all, how amazing it is and all the reasons why it's amazing, and I wanted to spend a little bit of time on that. In fact, I mean, I hear people sometimes describing this paper as, Hawking postulated the existence of a temperature of a black hole and all of its, thermodynamic implications. Well, one of the really amazing things about this paper is that Stephen didn't postulate anything whatsoever except general relativity and basic ideas of quantum field theory. Everything in the paper is derived by, well, non-trivial calculations in some cases and very tight reasoning. So what does Stephen do in the paper? Well, first of all, I mean, if you're looking to do something on a black hole background and something as difficult as quantum field theory, it would be natural to take the extended black hole background, which is very simple, static, Schwarzschild at least, and if you consider gravitational collapse, that's incredibly messy. But the problem with the extended Schwarzschild or other black hole spacetimes is they have a past horizon. And you'd have to give boundary conditions or initial conditions or specify a vacuum state on the past horizon. So Stephen realized the way to avoid that is to consider a gravitational collapse space-time, which, to start with, would seem to be making the problem much more difficult. He considers a scalar field to begin with and considers a spherical wave propagated backward in time. Now, that's not too intuitive to think of dynamical evolution of backward propagation in time, but you'd never get anywhere if you didn't do backward propagation. Stephen then realized that once this wave reached near the horizon, you could use geometric optics. Maybe that's not so non-trivial, but I probably had a couple of dozens of hours of conversations with people about whether that was really valid at the time of this, at this paper. Okay, then the key thing was to recognize the relationship between affine time and killing time once you were in the geometric optics approximation, so that you could propagate this wave further backwards. And there's an exponential relationship between those. So he gets then this wave that's propagated backward in time to past infinity, and that wave is quite unilluminating. You take its Fourier transform, and I would say that's also quite unilluminating, except that the positive and negative frequency parts are closely related. There's a logarithm that can be logarithm of the positive frequency or the negative frequency. He realizes the analyticity properties given by that, and realizes then what the log of the negative frequency, the minus omega portion was, and that gives this exponential factor that turns out to be a Boltzmann, interpretable as a Boltzmann factor. So he's done all that. He calculates the total particle number, and it's infinite. But that, he claims, is because of a steady rate of particle production over all time. He doesn't just say that. He introduces wave packets, redoes the whole calculation with the wave packet, shows that you get a finite radiation from each wave packet, and it's thermal if that wave packet is centered about a frequency. So now he has the thermal radiation. He, of course, realized, I mean, I say of course only for Stephen, that that's exactly what you needed to make black hole thermodynamics consistent, and that's exactly what you needed for the validity of the generalized second law. Okay, so I would imagine, if I could imagine somebody doing that, being, well, incredibly exhausted, but maybe having enough adrenaline to write it up and submit it for publication. Okay, but that's not where Stephen stops. He then argues that he did it for a scalar field. He argues, and seriously argues, because there are some differences, that this would hold for electromagnetic and linearized gravitational fields. And in the same paragraph argues this would hold for Fermi-Dirac fields, but there would be a change of sign because of the nature of the Dirac-like product versus Klein-Gordon product that would end up giving you the Fermi-Dirac distribution rather than the Bose-Einstein type distribution. Then he argues that this would hold for non-zero rest mass. He's argued only for zero mass up to this point. Then he argues in a very non-trivial argument that, in fact, his final answer only depends on the asymptotic final state of the black hole. He had assumed a spherically symmetric collapse to a Schwarzschild black hole, but that didn't, in fact, you only needed that the black hole settle down to a Schwarzschild final state, and that's not, I mean, that argument is you know, nearly a page or so of this. Okay, having argued that it only depends on the final state, then he was all set to do this for Kerr with superradiance and see what effects superradiance would give. So he did it in a paragraph for Kerr. Having done that, there's Reissner-Nordstrom. I mean, charged fields, how would they behave? They have a similar superradiant behavior. He did the Reissner-Nordstrom case and got the similar behavior there. Now, maybe he cheated a little bit in the end of that paragraph, just saying, for a general Kerr-Newman black hole, you get a combination of these effects, but it's true. That's what I mean, and I believe he did the calculation. Okay, then he goes on to back reaction. And he argues that the back reaction effects, now, mind you, there was no theory of stress energy, et cetera. Here only, I mean, there had been a little bit of work by Parker on particle creation and a little bit of formal work and so on, but problems like back reaction, this was really new. He argued that a freely falling observer would not see any large local effects in terms of particles or anything else. So this is the first anti-firewall paper, I think one can very safely say. If there are no large local effects, he argued that there must effectively be a flux of negative energy through the black hole. That has to match the flux of positive Hawking radiation energy at infinity. And he derives then that black holes must evaporate within a finite amount of time. And he draws the space-time diagram of an evaporating black hole. I think it's a shame that he didn't retain copyright on that, because there's really a lot he could have made in royalties every time that diagram has been written down since. So that's all in the paper. So I've said all nice things about it, but what about deficiencies of the paper, flaws in it? I went through the paper very carefully before this conference, just looking for things that were flaws, errors, or whatever. And there are three things that I have come up with that I wanted to mention. One, I mean, is certainly not an error. It's just the heuristic picture, and it's, Stephen says itself, that this has nothing to do with the calculation. It has nothing to do with the results. It's the heuristic picture that he has of particles, pairs of particles being created outside a black hole, and one of them tunneling in. The other one then possibly escaping or possibly falling back in itself. I don't like this. Other people, and in fact, may or well disagree, but the picture I would have is you've got sort of vacuum fluctuations, one of which is in the black hole always, the other is outside, and the one outside may escape as a Hawking particle or whatever, but I don't see any tunneling going in. But again, that's purely the heuristic picture that. The second thing is that Stephen believed at the time that there was not a well-defined stress energy for the quantum field. I mean, basically because of the ambiguity in particle number, which really is an ambiguity and really is there. But he had an image, or was picturing the paper, that stress energy for a quantum field would be a lot like a gravitational pseudotensor. You couldn't really talk about it locally, but you could still talk about its global effects. And again, this is not an error. It's being additionally conservative and making his task harder to argue what would happen in the back reaction, but he gives all the correct arguments in the back reaction. Okay, the third thing is the only thing that is genuinely an error in the paper, and the only thing that I can really criticize Stephen for. He misspelled the word gauge in 4 places. Okay, and so after 43 years of reflection and retrospective, that's all I can find to criticize in the paper, everything that I've just mentioned. And again, the first two are really not criticisms. It is, I hope I've made clear, at least through my enthusiasm, even if you didn't follow all the spherical waves propagated backward in time, through my enthusiasm, this is just an amazing person, amazing paper written by an equally amazing person. I've been thinking this for 43 years, and I'm really happy that this conference has given me an opportunity to say that. Happy birthday, Stephen.